Good morning all. We'll continue our discussion on slope stability analysis. Now in the previous two classes we have been discussing on slope stability analysis methods, what slope instability means, what are the forces causing instability, which are the forces which would resist instability. We had discussed factor of safety. Then we had moved to the first method of analysis, the basic one called phi-zero analysis. Later on, we moved to Swedish circle method, and now in this class we'll try to do the friction circle method. Now, friction circle method again has an assumption that the failure surface is an arc of a circle. Just like the previous examples that we had discussed, we have ADB and you have an arc of length L connecting A and B, and this arc is assumed to be a part of a circle. So obviously there will be a radius R and there will be a center O. Now the forces acting on this system will be number one, the self-weight of the soil. We had discussed it earlier as well. This weight will have a component which would induce an overturning moment with respect to O, right? So the first force is the self-weight of the soil, which will act at the centroid of the region ADB, like this. Let's call it W. Now the second force, which actually resists the failure, is the cohesive strength of the soil along the slip surface, right, C. It acts against the tendency direction of failure. Now the third force is reaction R, which acts on the slip circle. Now we had discussed this R in the previous section where we had dealt with the Swedish circle method, right? So even in this method you have a three system, W, C, R. You have a system where you have three forces. W will have a component there, second force is C, and the third force is R. Now W will have a tendency to cause failure by a moment with respect to O, and R and C will have components which would resist the failure. Now let's try to analyze the system. Now the reaction force on the slip surface will be at an angle phi to the normal at the surface, just similar to what we had discussed yesterday in Swedish circle method. You have a point here, you draw the normal, and reaction R will be at an angle phi with respect to normal, where phi is the angle of internal friction. Again, if you could just imagine one case, you have a point here, let's say it's point number 1, you have a normal there, and you have an R there. Now if I move to a different point, let's say point 2 here, you have a different normal there. These two normals will be pointed to the common center O, but these two normals will be of different inclinations, right? And obviously these 2 points will have reactions in different directions because angle phi remains the same, but the normal changes at every point because it's a curve. So fundamentally, as the slope of the slip changes at each point, the normal to the surface also changes. Hence we can say that the direction of reaction R also changes at each point along the slip surface AB. At this point you will have reaction R in this direction, at this point you will have a reaction in this direction. Likewise, each and every point changes its direction along the surface of the arc, and the normal changes its direction, and hence reaction R also changes the direction. Like this, you have an R there, you have another R here. Hence, you can have as many number of reaction forces as the number of points you consider along the arc. In general, you can assume these lines extended to be reaching near the center O. So once it reaches near the center O, you can assume there's an imaginary circle which is tangential to all these lines extended. Now that imaginary circle will have a center O and the radius r sine phi. In short, you'll have a circle here with center O and radius is equal to r sine phi. Such a circle is called as a friction circle. Now, in case of a purely clay soil, the friction circle will have r sine phi equal to r sine 0 radius, which means 0 radius, and that turns out to be just a dot. In case of C5 soils, where it's not purely clay and it does have a phi component, you will have a circle with center O like this and a radius equal to r sine phi. So that concept is called as a friction circle concept. Now, based on the friction circle concept, you can have these three values, these three forces acting. Number 1 is the weight, number 2 is the reaction, number 3 is the cohesion mobilized, right? So initially, just like the previous example, a slip surface is assumed and the weight W, reaction R are calculated based on the geometry that you've considered, A, D, B. Now, once we know the weight W and the reaction R, you can calculate the unknown mobilized cohesion C because it forms a force triangle. So knowing R, W and its directions, you can find out C by solving the force triangle. And once you know the cohesion, you can find the factor of safety as C dash by C, where C dash is the actual cohesive intercept or the cohesion intercept, and C is a mobilized cohesion. Now, just like the previous examples of Swedish circle method and phi zero analysis, this is just one iteration that we do up till this line. The next thing that you do is to take a different geometry ADB dash or ADBB dash likewise and do the iteration again and again till you get the least factor of safety value. And the slip surface which gives the least factor of safety value is considered to be critical. Now the next method is called Taylor's stability number and charts. Taylor determined the values of a term called stability number for finite slopes based on the friction circle method. If you have a slope whose angle is I and whose soil will have a friction angle phi, Taylor has given a set of charts from which we'll get a dimensionless number called Taylor's stability number Sn based on the slope angle I and the angle of friction phi. Now, stability number is equal to C by Fc gamma h. The terms are described here. C is the cohesion, Fc is the factor of safety, h is the height of the slope, gamma is the unit weight of the soil. Now this is an example, a chart given by Taylor where you have slope angle marked in the x-axis and different values of phi given as lines. So if you want, you can get a value corresponding to angle 40 degree of slope angle and phi equal to 25. So here 0.03 approximately will be the stability number. Likewise, let's take another example where let's say slope angle is 50 degree and angle of internal friction is 10 degree. So slope angle 50 is here. You try to see the value of Sn corresponding to angle of internal friction phi 15. So it turns out to be 0.12. Likewise, now if you want, you can refer the textbook by K.R. Arora, and in 453rd page the details are given. For examination purpose, the charts are usually provided. Now this is a tabular representation of something similar. You have angle of friction phi marked here and slope angle I marked here, and what you get inside is the stability number Sn. Likewise, if you have different slope angles I's and the depth factors df is marked here, which means h being the height of the slope, df multiplied by h being the total depth at which the failure occurs. That term df is called the depth factor. Now, knowing the depth factor and the slope angle, in short, knowing the geometry of the slope, you can get the stability numbers based on this chart as well.